Hello, everybody. Just getting started here. And let's see, there's the chat. Did I post tonight's PowerPoint? You know what? I think I forgot again. Darn it. Sorry, Kelsey, and everybody else. Usually when somebody says, did you post it, it means that I forgot. So sorry about that. Had a pretty busy day. I will post immediately after this, unless you want me to take a second to post it right now. I guess I could do that. Would that be helpful? And the recording from Monday is not accessible. Okay. Yeah, I can do that right now. Just take me a second. And let's see, course documents. Add an item. Lecture 23. April 22nd. Yeah, there we are. Okay, I'm posting it right now. Should be up in just a second. So Juan, the recording for Monday is not accessible. It's posted, right? Are you saying that it didn't work or it didn't run?
Right. It's giving me an error every time I try to access to it, but it's there. The link is there.
Was anybody else able to access the recording? Did anybody else try to access it and was unable to? Nobody's responding, Juan. I'm not sure.
Professor, I can't access the recording either.
Yeah, there we go. Okay. MP4, are you sure?
When I click on it, it says that I don't have access to look at the file.
That is very strange.
He posted it then?
Just tried same problem. Weird. There's not really any other way that I can do it that I know of. That's the full recording. That thing's like, I don't know, I forgot how many megs it is. It's a lot of, there's a lot to it. Do you think I should just try to post the audio portion of it, not the whole video? Can I post to YouTube? Oh boy. I wouldn't have a clue.
The video actually helps too. So I don't know.
All right. Well, we can see what we can do about that. Let's try again today. You know, because on my end of it, when I close out Zoom, it's recording right now, by the way. And when we close out the meeting, it says converting, and then I get 3 files, and and one of them is the biggest file is both the audio and the video. So you know, all this dancing around that I do here is on there as well. And then there's just an audio file that's just me rambling on. And then there's just a video file without the voice at all, but I don't see how the video helps you any more than just posting the PowerPoint. I don't know. Maybe I'll get with my kid this weekend and look at that YouTube thing. Yeah, I'll talk to him because he's home from college, so he's on the other end of this, and all of his professors are in the same boat I am. So let me see what they're doing, and I'll get back to you guys on that. Without any further ado, though, let's go forward with tonight's lecture. And what tonight is going to be about is this is the second part of our stress transformation lecture, where the first part, we went through the rigorous study of how to derive the equations so that we have 3 equations that correlate the stress on alternate coordinate systems. So the stress on the x prime, stress on the y prime, and the rotated shear stress. And each one of those is related back to the original normal stress in the x, the y, and the shear. Well, tonight we're going to explore how to do the very same thing in a graphic way. And also, hopefully, this might make it a little more visible or visual to kind of see what's going on as we're rotating these. So that's tonight. But before we do that, I want to talk just a quick little bit about ductile materials and brittle materials. So a ductile material, as we kind of talked about, I think we were physically in class the last time we talked about this, but ductile material is a material that you stress it, and this is a stress strain. It has an elastic portion, and then it has a portion of, the limit of proportionality, so it no longer is a straight line, and then it starts to yield. And then after it yields, it may have this strain hardening portion where it picks up more stress, and then eventually it will fracture. This is the ductile path. So ductile materials fail due to shear stress. This is just a generality. Ductile materials fail due to shear stress. So if you put a torque on a round bar made of a ductile material, when it fails, it basically just shears on a nice clean surface because it's the torsion is producing a shear stress. When the shear stress exceeds the material's shear stress capacity, it fails in shear. And so you get a nice clean break like this. So a torsional failure will cause a smooth, flat failure. And if you put it in tension, a tensile test on a ductile material, well, the material necks down. That's what I'm showing here. So it actually starts to neck down as it's elongating. But once it actually fails, it's kind of hard to see it in this, but there's like a little cup in here, and there's a little round ball on this side, and the surface is actually like a 45-degree crater in here because it didn't actually fail in normal stress, it failed in shear. And tensile loading causes section to neck down and fail with a characteristic cupping due to shear stress. On the other hand, brittle materials tend to fail in normal stress or tensile stress. So here, the red line is the path of a brittle material. It kind of never really has a straight line portion to it, but it just rises, 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 and then very suddenly will fail. That's the definition of a brittle material. And a brittle material could be concrete, not reinforced concrete, just concrete, or rock, or other natural materials, or even some metals are somewhat brittle, like iron is a pretty brittle material. So if you put a brittle material in a torque, it's actually going to fail at a 45-degree angle because this is a diagram, this is our little stress element. And what it's saying is that it has plenty of shear stress capacity, but it's going to take this rotated coordinate system and fail along the principal stress of tension. This is why we're talking about principal stresses, because the material, if it is weakest in tension, it will find that rotation that produces the greatest tensile component, and that's what it fails on. So in this case here, that's why it's at 45 degrees, because if you rotate this 45 degrees, you get the maximum principal stress. Torsion failure due to a normal stress causes a characteristic 45-degree failure surface. If you want to see this, in fact, I still remember this like yesterday. When I took this class as an undergrad, the professor, and you're going to laugh, this is back in the days of chalkboards. He actually had chalk in a chalkboard, but he took out a big stick of chalk and he goes, all right, you don't believe me? And he twisted that piece of chalk and it broke, and he passed it around the class and it looked exactly like that because chalk is a brittle material. Another real-world example. This is the failure surface of a front axle shaft from an undisclosed location of a Toyota 4x4. Front axles were not the strongest axles on the planet. And so this is an example of a broken front axle shaft. From this diagram, would you say that my front axle shaft used to be brittle, or did it used to be ductile? And the answer is it was rather brittle. So it failed in this is a 45-degree, it's kind of hard to see, you gotta have to hold it in your hand, but it's a 45-degree failure surface. And the grain of this, you can kind of just see that it is actually a tensile failure. It fails in normal stress. Here's axle shaft number 2. And I try to get a different view of it, but this again is what's known as a brittle failure, and there is a 45-degree surface on this at some point. So again, axle shaft number 2 was also brittle. I threw away axle shaft number 3. It was too big. It had a whole sprocket still attached to it. So I didn't get a photo of axle shaft number 3. I know what you're all thinking. How many axles did I go through? I went through 3 before I finally ponied up and got a whole new axle housing and chromium, chromoly, super duper warranted for life axle shafts, and then I never broke another one. And so if you take a brittle material and you just pull it, picture this could be, like I said, iron, or this could be just a cylinder of concrete, and you put it in straight tension, it will fail in a clean break, just like that. Okay, any questions on brittle or ductile materials? Anybody wondering why a steel axle shaft was brittle? And yes, why? Oh, from heat. Yes. Steel axle shafts were hardened. So what they did is they took steel and they hardened it through various processes of heat treatment and whatnot. And so the point was to make that axle strong. They really were trying to maximize the strength of that axle. But whenever you take a raw material and you either cold work it or you heat treat it or you do these various industrial processes to raise the strength, you always give up ductility. So actually I can go back. I won't take too much time on this, but right here, the blue line and the red line could actually almost be the same material. If I do this, the blue line might be the raw steel in a very ductile form, but you could take the raw steel and you could cold work it or heat treat it. And this is the final strength there of the ductile material. This is the yield of the ductile material. And you can work it so that you can really get that strength up much higher than it was before. But what do you give up is ductility. And that's always kind of the metallurgical compromise. Do you want it to be ductile or do you want it to be strong? There's ways to kind of get a little bit of both, but usually one or the other. You can take steel and put a little bit of carbon in it, and it's a fairly strong but very ductile material. Or you could take steel and put a lot of carbon in it, and all of a sudden it is immensely strong but very, very brittle. And that's why axles can be brittle, is because they're going for strength. Okay. Moore's circle. This is our graphic way of describing stress transformation. So it's a graphical representation of plane stress through the transformation angles. Starting with our equation for transformed normal stress, this is our result from last time, that sigma x prime is equal to, this is basically the average stress, and then the transformation of the cosine and sine. We can start with this equation and the transformed shear stress, tau x prime y prime. And by squaring and adding each equation, we can eliminate theta. So we can combine these two equations and basically wash out theta. And by doing so, we get this, a squared term and a squared term, squared term, squared term. And since sigma x, sigma y, and tau xy are all known constants of the problem, those are all the problem statement, that's the beginning of the problem, then we can rewrite this whole thing as sigma x prime minus sigma average squared plus tau x prime y prime squared is equal to r squared, where sigma average is sigma x plus sigma y over 2, and r is equal to, so I just basically squared this whole part, rewrote this. So the radius is going to be the radius of a circle is equal to these terms in here. And sigma average becomes the center of the circle, and r becomes the radius of a circle. That graphically represents the transformed stress state. Any questions so far? Okay, so how do we do it? How do we plot Moore's circle? First, we construct a positive coordinate system. And this is the part that usually throws everybody for a loop. This horizontal axis is normal stress. The vertical axis is shear stress, and it is positive going down. Why is it positive going down? Because if Mr. Moore had made it positive going up, then it would have the wrong direction in the positive rotation. I think that's why. So really, this is just the way it has to be in order for it to make any sense. So, but remember, positive down for the shear stress, positive to the right for normal stress. Positive normal, positive shear. The angle on this circle that you're about to see, the angle that's in this circle is going to be 2 theta. Just like in the equations, it was 2 theta. This angle is going to be 2 theta. Again, sigma x, sigma y, and tau xy are known constants of the problem. So we start by plotting the center C on the sigma axis. So this is 0, 0 at the crosshairs. And so we go in the positive direction, sigma x plus sigma y over 2, sigma average. Next, we're going to plot our reference point A at sigma x tau xy. Remember, these are known quantities from the problem statement. So I can go, if sigma x is positive, I can go over sigma x, and I go in the positive direction. If tau xy is positive, I go in the positive tau direction, and I plot point A. Then if I connect a line between C and A, this is called my reference line. And this reference line represents theta equal to 0. It might be a little confusing. Let me try to pause here for a minute. Remember our original element looked like this. And this is x, and this is y. And if you do a rotation, then do a different color here. If I rotate the coordinates like so, then this is x prime. And this is the angle theta between the two. Okay, well, if that angle between the two is equal to 0 degrees, then x prime is equal to x, right? You haven't rotated at all. That's what this point is right there. That is at a rotation of 0. So the stress at this point right here is the stress at the original coordinate system. Now, hopefully this will make a little more sense in a minute, but that's why obviously this angle to the horizontal is not equal to 0, but this is the reference line. This reference line represents the original orientation of the grids. Any questions about this before I wipe this out?
I have a question.
Yes, please.
So could you, like, for the sake of it, could you take points C and A and just like move them to be on the x-axis? Is that basically what it is?
Not exactly, but good question. Good question. So we start the problem, getting funky with these graphics here, but this stress was our original sigma x, and this shear stress was our original tau xy, and those are valid at theta equal to 0 degrees. We haven't rotated at all, so this is sigma x, tau x, and I plotted those. So this distance is sigma x, and this distance is tau xy. So that's why this reference point is at 0. What we're going to do is we're going to build a circle around this point, and every point on that circle is going to represent some other rotated coordinate system. But this is just our starting point. This is our home plate. Does that help?
It does. It still doesn't make a whole lot of sense, but I can kind of grasp what we're like leading up to.
Okay. Well, let's forge ahead. And please, for all of you on the call, please ask questions because I don't know where to elaborate if I don't know where you're hung up. But let me do that and let's forge ahead. And hopefully this starts making sense. So the point is, point A is where we start. This is our original set of stresses and we haven't rotated at all. So the next thing that we do is we draw a circle. The circle is centered on C, and the circle has a radius such that it goes through this point here, which we plotted with our original stress condition. The radius of this circle, as we found earlier, is sigma x minus sigma y over 2 squared plus tau xy squared square root. That's this distance right here, which if you run this number is an actual number. It's so many KSI. Okay, so now we're going to add points B, D, E, and F around the perimeter of this circle. And let me kind of reiterate that when you move along this circle in an angle, then that angle that you're moving, you're transforming the original system, you're rotating it by that angle. So point B represents an angle that is this much of a positive angle. Counterclockwise is positive. So to get from A to B, you have to rotate this many degrees. But remember, this is 2 theta. So you're actually rotating half this many degrees to get to B. And then you're going to rotate this many degrees to get to F, D, and eventually E. These are all rotations around this circle. So if I have an arbitrary point G, G represents the stress at some x prime and tau x prime y prime coordinate system, and G has been rotated in the positive direction by theta. What I drew on the circle is 2 theta, but what's actually been rotated is theta. Okay, so these points here, point B, the significance of point B is that, first of all, there is no other point on this circle that has a greater normal stress than B. B represents the maximum possible distance you can get from 0. So B is the principal stress, 1. That is the largest normal stress that you can get. It also, notice it also represents at the same time exactly 0 shear stress. So like we said last time, at the point of maximum normal stress is also the point of 0 shear stress. And you can see that right on the graph. That is a typo. That should say minimum. The minimum normal stress, sigma 2, is located at D. Same theory, but at point D, there is no point lower or further away from the 0 in the negative direction than point D. And there's no shear stress at D. D is right on the 0 line for shear stress. The maximum shearing stress is located at point E. There's no other point on here that's further down in the positive shear direction than point E. And at the same time that you have the maximum shear stress, you have the average normal stress, as you can see here. And the last point, point F, is the minimum shear stress that was also located at the average normal stress. So these are the important coordinate points on this circle. In the last lecture that we did, in the last problem, one of the last things we did is we solved for these points. We solved for the maximum and minimum normal stresses. We solved for the maximum and minimum shear stresses. And we also solved at what angle did those occur. And we got like 44 degrees, -3 degrees, so on and so forth. Well, that is this distance here. The -3 degrees is right here, and here, and here. So again, this is a graphic representation of exactly what we did in our last lecture. Point G represents the transformation from x to x prime. This, again, the reference line represents our starting point at x, and G represents an arbitrary new coordinate system at x prime located theta away from A. The blue line is reference for x, the red line is the reference for x prime. Angular distance between is the angle of transformation measured at 2 theta. So again, I'm hoping I'm not confusing this. What's on the graphic circle is 2 theta. What's in the actual transformation, what you would use in your equations, is theta. So in other words, if the actual transformation angle that you're looking for is 45 degrees, then what you would do here is go 90 degrees. 2 times 45 degrees would be 90 degrees, so you'd actually go all the way around to this point. If a point A represents the original stress sigma x tau xy, then point G rotated by 2 theta represents a transformed stress sigma x prime tau x prime y prime. Clockwise rotation represents positive theta rotation, while counterclockwise is a negative theta rotation. Point H represents sigma y. So remember, sigma x was down here. Sigma y is located on the circle 90 degrees from sigma x. So 90 degrees on the circle is 180 degrees, 2 times theta. 90-degree transformation angle is plotted at 2 theta or 180 degrees on Moore's circle. Okay, any questions, or are you guys ready for the first example?
I have a question.
Yes.
Is there any significance to the points at like maximum shear stress and no normal stress on the circles? Like, do they have any significance in equations, or no, not really?
No, they do. They do. Remember the last lecture, one of the last things we did is we talked about principal stresses, and we came up with a inverse tangent is equal to theta p, and we solved for theta p. And then we had this rather ugly equation that solved for sigma 1, sigma 2. Well, sigma 1 is this point right here. Sigma 2 is this point right here. Then we've had a tangent or inverse tangent is equal to something, something, and it gave you theta s, the rotation to get to the maximum and minimum shear stress. And then we solved for tau max and tau min, cranking out the equation. Those 2 points are E and F. So yeah, there's a significance to the 4 corners is graphically representing what we just solved for in our last lecture.
Okay, thank you.
Did that hit it, or were you looking for something else?
Well, you were talking about like point E and point F and H, right?
Yes.
I was talking about no normal stress, but the maximum minimum shear stress. So on the tau axis, is there any significance to those points where they meet the circle?
Oh.
Yeah.
Oh, okay.
That
Okay.
was my question.
So you mean like right there?
Yes, right there.
Okay, okay, okay. No, there's not. There's no real significance to that because that's not a maximum shear stress. That's the maximum shear stress at zero normal stress here and here, but it doesn't give you the maximum. The maximum is here and here. At the end of the example, I'm kind of blowing the big surprise here, but the example is exactly the same problem we did last lecture. I didn't get very creative about it. So we're just going to do a Moore circle for the same exact problem that we found all those points for on before. And I'm going to re-show you all those points. So you'll see where this point is. You'll see where this point is because it's going to be the points that are closest to the normal being 0 and the shear being a positive or a negative value. But other than that, no, these aren't special points.
Okay. All right. Thank you. That was my question.
Okay, good. Any other questions before we get to the example?
I have a question.
Yes, please.
So clockwise rotation is positive and counterclockwise rotation is negative?
Correct.
Okay.
No. Wait, what? Say that again?
So I'm just reading off like the PowerPoint. So clockwise rotation is positive.
No. Clockwise
Oh.
rotation is negative.
Oh.
Counterclockwise is positive. Did I do that backwards?
I was reading it off the PowerPoint. If you slide, yeah, right there actually.
I did that backwards.
Oh. Okay.
Oh, yeah.
So
Counterclockwise is positive.
okay.
Clockwise is negative.
All right, got it.
Yeah, I gotta fix that. Okay, thank you. Thank you for bringing that up because that's not what I said and that's not what I meant to say.
Can you repeat where the typo was again?
Of course, of course. Slide 56. Slide 56, and it says clockwise rotation represents positive while counterclockwise is negative. It is the exact opposite of that. In fact, that is so grievous that I'm going to fix it right now. My mouse represents So if you download the PowerPoint presentation that I just posted at the very beginning of this class, that was slide 56, and you can reverse those. Okay, so example 1. Following figure, draw the Moore circle. You will recognize this from the last lecture. We have 5 KSI tension in the X, 3 KSI tension on the Y, and a positive 8 KSI and shear stress. And we want to use Moore circle to find the sigma x prime, tau x prime, y prime for theta equal to minus 40 degrees. Okay, so we're going to have to draw the circle. So to start drawing the circle, we're going to find the average. The average is 4 KSI. We need to find the radius. The radius is 8.062 KSI. And so we start with our positive coordinate system. We put our center at 4 KSI. We put reference point A at sigma x, tau xy, which is Sigma is the horizontal, so that's 5, and positive tau is down, so that's the 8. And we draw our reference line from point C to point A, and that represents theta equal to 0 degrees. And then we draw our circle with the radius of 8.062 KSI. And this is actually, there's one benefit of using PowerPoint. When I drew this on the dry erase board, it was very difficult to get this to be a circle for one, and to be to scale. So this is actually drawn to scale. So now I found all of these reference points. Point B is, you know where point C is. This is that average of 4 KSI. So the average plus the radius gives you the 12. F here is the average, but the shear is 8.062 and up is negative, so that gets you there. Here the shear is equal to 0, and you take your average minus your radius to minus 4.062. And finally, E is again horizontally at the average of 4, but you go down the radius to get to a positive 8.062 KSI in shear. Any questions so far?
Can you say that one more time, please? I don't think I got it. Or
Okay, so the radius we found last slide, right there. The radius is 8.062. And C is 4 KSI from the 0 point. So this is 4, and the radius is 8.062. So with that, you can go 4 plus 8.062 to get to 12.062. You can go 4 and then up gives you minus 8.062. And then 4 minus 8.062 is minus 4.062. And E is at the average of 4, but you go down, which is positive 8.062. So you can find the 4 corners by using the center and the radius.
all right, thank you. I got it.
And after I just said all that, I forgot I wrote it all out. So here is exactly what I just said. Oh. Give me another moment for this slide. So basically, I just wrote out exactly what I had just said. Okay, so on the Mohr circle, remember this point here represents 5 KSI over, 8 KSI down. If I go 90 degrees, which on Mohr circle is 180 degrees, and I plot this point here, then this is going to be 3 KSI and minus 8 KSI, which it is. So I did it in CAD, everything's to scale. So I verified that this actually lands where it's supposed to land. But go up a few slides here. The original, see, this is sigma y. Sigma y is 90 degrees from sigma x. Sigma x was 5 KSI. If I rotate 90 degrees, I should have 3 KSI. So here I've rotated 90 degrees and I plotted that point and then just measured it in CAD, and it is indeed 3 KSI minus 8 KSI, which is sigma y. So sigma y is always out of phase with sigma x by 90 degrees. Theta equal to 90 degrees or 180 degrees on the circle. Okay, now back to the problem statement. We want to find sigma x prime, tau x prime, y prime at a minus 40 degrees. So minus 40 degrees is clockwise. Clockwise is negative. That's why it's very important to fix that. And so I drew on here minus 40 degrees. Now, again, theta is minus 40 degrees. So what you're looking at on this graphic representation, this is actually 80 degrees between these two. What we want to find is using geometry now. Instead of just plugging through the two equations, use geometry to find where is this point G. So if I transform my coordinate system by minus 40 degrees, what do I get for sigma x prime, tau x prime, y prime? So I draw the point at minus 40, which is at 2 theta or minus 80 on the circle. We cannot solve for the point G directly, graphically on the circle. So we have to break this angle into parts. And the reason why I can't solve it directly is because this is measured from this reference line. And the reference line, I can't really use geometry to find from the reference line directly. So we're going to break it into two parts. What I can find is the angle from the reference line to a vertical. And that gets me to a right triangle. So point A here is, well, basically what I'm doing is rise over run. So the run is 5 KSI minus 4 KSI. So this is over by 1 KSI horizontally. And vertically, from 0, it's 8 KSI down. So that gives me the angle of this triangle. Do the inverse tangent of 1 KSI over 8 KSI, and I find that this angle right here is 7.125 degrees. So I drew it on there. Now I want to find this angle. Angle psi is found by looking at the total geometry. So what I have is between E and D, this is 90 degrees. That's a right triangle. That's 90 degrees. And then I add to my 90 degrees the 7 and the 8th degrees that I just found. And then I subtract from the whole thing the 2 times the 40 to get me to this line here. And that leaves me with 17.125 degrees. That's this angle right there. Do I have any questions about that? So the strategy is find how far you are from a horizontal or a vertical, and then use that to get the missing angle. What you need is the angle between where you want to be and a horizontal. Okay, so now I have all this information. I know that the radius is 8.062 KSI, and I know that the angle is 17.125 degrees. So with some trigonometry, I can find that sigma x is going to be 4 KSI minus cosine 17.125 times the 8062 gives me to minus 3.705 KSI, which is this distance right here. And, oops, tau x prime y prime is 0 degrees or 0 KSI. I start at 0. And this vertical distance here is the sine of 17.125 times the radius of 8.062 to give me 2.374 KSI. Everybody okay with my trigonometry?
Professor,
Yes.
can you go over again on how you get a 17.125 degrees?
Okay. So we got the 7.125 degrees here. Did that make sense?
Yes.
Okay. So if you got this, then I can do a little scribbling here. I want to find psi. That's what I need in order to use sine and cosine to get to this point. But what is psi? So you have to look at what do you know? What you know is from horizontal to vertical is 90 degrees. And I mean actually 90 degrees on the circle. And you know that this is 7.125 degrees from what we just did. So now what you know is this angle all the way to this line, A. But you also know the angle, use a different color. You know the distance from line A to this line here. You know that because that was the problem statement. That's minus 40 degrees. But minus 40 degrees on the circle is minus 80 degrees. So now you just add it all up. You have 90 plus 7 minus 80 gives you 17.125 degrees.
Got it. Thank you.
Okay. Okay, so that got us that angle. Once we have the angle, then it's just straight up trigonometry to get the horizontal and the vertical. And the vertical is measured from 0, so the vertical is the shear stress. The horizontal is measured from your center point, so you got to take the 4 KSI out of it, and that gives you to the horizontal to this point here. And the horizontal is the normal stress. The vertical is the shearing stress. So that gives you this point right here. We've solved for it using geometry. So now from Moore's circle, we have all these points. Point A is our original sigma x, tau xy. Point B is our maximum normal. Point F is our minimum shear. Point D is our minimum normal. Point E is our maximum shear. And then we have solved for point G. And point G, by definition, theta is minus 40 degrees. So we drew it on the circle as minus 80 degrees. Okay, this is the same image. And so here's our friend. This is all the stuff that we solved for last lecture using the equations. So I'm going to plot those on the circle here so you can see how this works. So at theta equal minus 90, which is minus or positive, actually it doesn't really matter, does it? But minus 90 on the circle is minus 180 degrees. So that gets you to the red dot. And the coordinates of that red dot is 3 KSI over minus 8 KSI up. The next dot that we found was minus 70. So we're actually going this way, right? Minus 70 is minus 140 degrees on the circle. And these are the coordinates that we found from the equations. Do they make sense? Yeah, that's minus, about minus 2 right there. And this is minus 5.5 going up. Okay, before I keep going around the circle, is everybody tracking with me? Does this make sense?
Yeah.
Go ahead, Caesar.
Oh no, I'm saying like it makes sense.
Okay, good. Anybody having trouble? Okay, so what I'm going to do is go around the circle with all these points that we solved for from the last lecture using the equations. So at minus 50, Again, this is minus 100 degrees on the circle, so that's minus 50. And what we solved for was a normal stress of minus 4 and a shear stress of minus 0.4. You see how small that is. And so basically what I'm graphically showing is all of these answers that we got last lecture from the equations actually make sense on the circle. It all kind of falls together. I can go minus 48.56, which is what we found last lecture was sigma 2, the principal stress where normal is minimum. So there's your minimum normal stress. You have 0 shear stress, and you've gone minus 48.56 degrees, which is this distance here, which would be double that. So just a little bit more than minus 90 degrees. At minus 40 degrees, we just solved for this point here. Minus 30 degrees is here. Minus 10 degrees is here. So we got a normal of 2 and a shearing stress now 7.8. We're getting pretty high on the shear stress. Here's point E at average normal maximum shear stress. And that's only 3.5 degrees. So that's why this was 7. We just found this to be 7. That's twice the 3.5. At 10 degrees, we're starting to drop down from our maximum shear stress, and we're picking up a lot more normal stress. 30 degrees, now we're getting very high on our normal stress and getting lower on our shear stress. At 41.44 degrees, we have maxed out the normal stress. We are at 0 shear stress. 50 is here, 70 is here, and 86.44 is our minimum shear stress and our average normal stress. And then we're back to 90. So we've gone all the way around in the circle, hitting all of these points, and you can see how they fit. Most of these numbers we found from the equations, except for the minus 40 that we just did from the geometry. So that is Mohr circle. That's how that works. And it can be very useful for either finding points, if you don't want to find them from the equations, but it's actually probably most important just in the visualization of, as we're rotating through circles, all you see is that one angle that you're looking at if you use the equations. But with Mohr circle, you can see the whole thing right in front of you. You can see where your maximum normal, minimum normal, maximum shear, minimum shear, and any point in between. You can see them all on the circle. Do I have any questions?
So is Mohr's circle like a little bit of a different way of like analyzing like a stress element compared to what we learned on Monday?
Yes, it is.
Oh,
It is, the analogy is when we did shear and moment diagrams. We first did shear and moment diagrams by making section cuts, finding free body diagrams, and finding the equations for the shear and the
yeah.
equations for the moment. Then we learned how to do it the graphic way. And it really is the same thing, just the graphic way kind of illustrates the whole thing in front of you instead of just looking at equations. And it can, in some cases, be a quicker way to do it. This is the same analogy.
It's a good analogy. See?
Good.
All right.
Any other questions on Mohr's circles? We will see this again. I'll give you a little precept. What we're going to do next is, this was all stress transformation. What's coming next is strain transformation. They're not the same thing. And then what we're going to do is we're going to look at Mohr's circle again to quantify strain in the normal direction and in the shear direction as opposed to stress. So this will come back for another section. Okay, so we got a little extra time. Does anybody have any other questions, anything that's bothering them that you'd like to talk about before we close out this session? Nobody? No questions at all? Okay. Just as a reminder, I'm doing office hours from 4:30 to 5:30 basically on the Monday and Wednesday. It's a Zoom session. I've been posting those on the day. And if you have questions that you don't feel comfortable talking about in front of the whole class, by all means, get me on one of those Zoom sessions and we can talk more in private, whatever is on your mind. And that is basically, unless there's any other parting thoughts, that is basically what I have for tonight. Will do, Ryan. Thank you. All right, everybody have a great weekend. And oh, don't forget, homework 12 is due next Monday. Please don't forget. And everybody have a great weekend. Thank you.
Professor, before you go,
Yes.
I have one quick question.
Sure.
I wanted to wait until everyone kind of left. But can you go back to slide 99?
Can you still see the screen?
No, I cannot.
Okay.
There we go.
You can see it? Okay.
Yeah.
And slide 99?
Mm-hmm.
Okay. Okay.
Yeah, that one. So I feel like I'm having kind of a hard time like thinking about how we get from point C to point G, but I guess my brain wants to think of it as like think of the radius as like a vector, and we start from point C and we just kind of find that coordinate on G with like 4 KSI, that's your starting point, and then you go back in this normal stress direction with like your cosine. Like I know it's kind of the formula, but is it okay to think about the radius as like as a vector, or is that kind of like counterintuitive?
Well, I mean, ultimately, the best answer is whatever works for you, of course. You know, however your brain sees it, then you see it, and then that's great. It's better than not seeing it at all. But the way that I taught it and the way that my brain sees it is I see it as a triangle. So this is
your 17 degrees.
Yeah, so there's an angle in there that's 17 degrees.
Mm-hmm.
And if I have the hypotenuse, this is how I learned it, but this is opposite, adjacent. Boy, I cannot write with this thing. Opposite, adjacent, hypotenuse, and an angle.
Mm-hmm.
Angle psi or whatever. And so even though the circle is doing something like this, that doesn't matter anymore. We don't really care at this point about the circle. All we're looking for is that point.
Yeah.
And we're only looking for a vertical dimension to that point, and we're looking for a horizontal dimension to that point, because the stress at that point is defined. This is tau, and this is sigma.
Mm-hmm.
So we're just looking for the horizontal and the vertical components of that point in order to label it tau and sigma.
Okay.
And your zero normal stress happens to be there. That's the only complicating part. That's why you have to go 4 KSI minus the horizontal component. But if you, I'm sorry, go ahead.
At that blue dot that you just drew, that's where our C was, or that's
That C, but where that dot is right there.
Oh, okay, okay.
That's your point of zero normal stress.
Mm-hmm.
So you have to shift it. You know, you're finding this length.
Yeah.
But what you really want is this length. So you find this length first, which is cosine 17 times 8. And then you subtract, or you go the other way because it's going negative. But you got to get that 4 KSI out of there.
Okay. And we'll see, C will always be on the normal stress axis?
C will always be on the normal stress axis. Yes.
Okay.
It may not always be positive.
Mm-hmm.
Certainly, there's no reason that it needs to be positive or negative. It could be either one of those.
Mm-hmm.
But it will always be on the normal stress axis. Yes, that's the definition of the circle.
Okay, then yeah, the way my brain wants to think about it is basically take the radius, think of it in terms of like just X and Y components for the normal stress and shear stress.
Mm-hmm.
So, okay.
Mm-hmm. But if you think of this as a vector, if you're liking to look at this as a vector, then what we're talking about is really the resultant or the components of that vector, which really yields you the same result.
Yeah. Okay. That really helps. Thank you.
Okay. You're welcome.
I had a quick question.
Sure.
So with more circle, with like points in the circle, do you have to go from like A to G? Like when like determining the amount of points on the circle that you do the calculations for?
Well, yeah, you kind of do, because let me erase some of this out. I'll tell you why. The special significance of A is your reference line. A represents zero rotation. Okay. So if you have a rotation in any direction, if you have a rotation, it's from your reference.
Yeah.
So when the problem said minus 40 degrees, you have to start at your reference and go minus 80 degrees on the circle. But that's why you had to start at A. And then once you get to this point here, you kind of have to find your way from A to here, because it's only A do you really know where you're at.
Okay.
But you could use geometry. I mean, I suppose that if you, okay, so yeah, that's the problem. If you go from, say, E, you don't have anywhere to start. You don't have a foothold, because you don't know what this angle is from E.
Mm-hmm.
That angle was measured from A.
Yeah.
So that's why you have to go back to A.
Okay. Yeah, because I was looking at the book, and I guess like they all do like a certain number of points. Like they don't all just do it like in that exact same layout from A, B, C, D, E, F, G. I guess they do it a little differently, but I see what you're saying though. I mean, point A is like, that's with reference to like the radius that you end up calculating, or the R value, I should say. The R value that you calculate.
Yes, but it's also the original problem.
Yeah.
Sooner or later, I'm going to get better at this. The original problem is given to you like this.
Yes.
That's zero rotation. Mm-hmm. And the original loading is given to you. Let's see, do I do it this? No. Anyway. Okay, so you start at the arrowhead. No, you go that way. There. Okay. Anyway, this is your original normal stress. This is your original shear stress. So this is 0. So any rotation from 0 is from 0. A is the reference line. A represents 0. So if you're going to go a negative, you go this way. If you're going to go a positive rotation, you're going to go that way.
Okay.
Always going from A some direction.
All right then. Yeah, it makes a little more sense. Well, I'm sure I'll get it down once I start like working out problems and stuff like that.
That always helps, yes.
Yeah. All right, but thanks. Appreciate your help.
Okay. Anybody else before we close it out? Okay. Thank you very much. We'll see you all next Monday.